Good afternoon. Across the world, increasingly natural disasters are more prevalent and more serious. Imagine that you are one of the thousands of people affected by looters targeting homes in the aftermath of Hurricane Katrina, or the tens of thousands of households that saw the California Camp Fire encroach upon your front yard last year, or among the hundreds of thousands that saw their homes flooded and themselves stranded on the roofs of their houses after Hurricane Irma. In all these situations, our first instinct is to call 911, call for help. Hey, we need help. The government is here to help us. However, what we do see is that those situations that cause the biggest need for natural disaster help are also the ones that cause the biggest breakdowns in communication. 60% of the affected areas of Hurricane Katrina, 55% of the Camp Fire victims, and 29% of Hurricane Michael victims saw extended breakdowns in internet and cell coverage for at least 1 month after the disaster. In the aftermath of the disaster, it's impossible for people that need the help the most to get it unless they have the ability to reach out and ask for it. Government agencies, emergency responders alike, rely upon effective communication to reach out and make sure that they can provide the aid to those who need it the most. Now let's talk about Puerto Rico, a particularly egregious case of how communications breakdowns resulted in poor recovery post-disaster. In the immediate aftermath of the hurricane, 95% of cell towers went offline, and 85% of telephone and internet cables were destroyed. 47%, just under half of the citizens, still lacked basic electricity over 1 month after the disaster. Now, what happened and why is this still an issue? The communications response team that kind of addresses disaster recovery has a current palette of solutions, which primarily consisted of mobile cell sites and other methods of restoring conventional cell coverage post-disaster. However, what we did observe was that because of the lack of a power infrastructure post-disaster due to the wholesale destruction of all power generation facilities on the island, they were unable to actually sufficiently provide the electricity they needed to fuel these kinds of solutions that are conventionally deployed. And we do observe is that it took about 65 weeks for the island to reach 80% cell coverage in the aftermath of the storm. Our solution, peer-to-peer chat, is designed to address these kinds of stopgap, ad hoc needs for communication in the aftermath of the disaster. What we are proposing is an integration of two separate solutions that are typically used in disaster situations: peer-to-peer communications, as well as long-range hardware radios, into a larger solution that is more deployable for civilians and responders alike. So let's start with talking about what peer-to-peer is and how we actually leverage it. Peer-to-peer is this idea that you don't need the internet to send files back and forth between phones, right? I can have my iPhone and look at your iPhone, and I can airdrop a file directly to you. That's the idea of peer-to-peer. That you can, without internet, basically share files and information back and forth. However, the big drawback to peer-to-peer technology that has prevented it from being adopted for disaster situations is the extremely low range, right? There's no way for me to airdrop a file to someone that's like 2 doors down, or even across the wall from me. And that means that it's really quite unviable for us to use peer-to-peer to address something like the Puerto Rico situation. So what we have done is we've added on this idea of long-range hardware radios that integrate into peer-to-peer meshes. So instead of just having disparate groups of people that can only communicate within each other, we install these hardware radios that become part of the network and then connect disparate groups together into one larger peer-to-peer group. We envision this being used to deploy across all of some situation like the Puerto Rico aftermath to allow people to communicate together in an effective ad hoc fashion on a rapid response basis. So we deploy firstly in backbone, in the most dense regions, urban centers, etc., where each backbone node can reach the maximum number of people. And then secondly, prioritizing those regions most drastically affected by the disaster, in this case, the path of the hurricane itself. And then finally, deploying to the entire island so that we have an entire communication network that is rapidly deployed across the entire island that does not need a rigorous backbone, a rigorous infrastructure of power deployment across the entire country. So the two-pronged approach to our solution is in two main deliverables. Firstly, a mobile application that kind of implements all of the peer-to-peer networking, the kind of enforcement of routing tables, etc., that allow us to communicate back and forth to individual users without the need for internet. And secondly, our key innovation here is the idea of backbone nodes, right? These hardware radios that have the ability to extend to a larger audience, right? So these two backbone nodes are able to use their radios on board with antennas to communicate over theoretically very long ranges, up to 6, 10, or infinite range, 6, 10, or infinite range, depending on the communication protocol that you use. We'll go into more detail on that later. All right, so now let's talk about what we actually accomplished and show you what we've done. So what we have here on the left is a DocuCam of one of our clients here. So this is a phone here, and it is in airplane mode, so there's no way it can access the internet. And secondly, we have our fifth group member, Ben, here in a different area that is not reachable through peer-to-peer technology. And what we've done is we've deployed two different backbone nodes, one here and one with him. So we're going to leverage this backbone network to allow us to chat back and forth without the need for any internet access. So,
Yeah, and so
Keep talking.
yeah, so the key thing here is that there's no need for us to explicitly enforce any sort of joining into the network. So we can just kind of drop in these backbone nodes into the area, and therefore you don't need users to be explicitly informed about the presence of these. So you can just on the fly join these networks and not have to worry about any sort of like, oh, I'm joining XYZ network, I'm paying for XYZ service. This is something that we envision government agencies or first response organizations deploying on the fly in terms of just airdropping or hand dropping them into certain areas. The power requirements are very low, and there's no need for any external equipment. So we don't actually need to supply any sort of large infrastructure for this to be deployed on an ad hoc basis.
These are out of the range of traditional peer-to-peer completely.
Right. So right now we have the back and forth chat. The text is a little harder to read on this. All right. So now let's dive into more of a technical overview of what we've accomplished and how we actually did it.
Great. So I want to emphasize the difficulty of what we're trying to accomplish. So with mesh networking, the routing can be very unstable because there are a lot of connections going on at the same time. But with disaster relief, we really want the robustness and reliability. Even as people move around, there are new connections, they go in and out of range of each other. So we've designed a custom protocol given our client users using the phone just connected via Bluetooth, and our backbone nodes that have that stronger, longer network between them. So I'm going to talk about this protocol in some more detail and how it brings unprecedented connectivity and coverage to disaster situations. So let's consider a portion of that network that we just saw. We have two clusters of clients who they have no cellular service, no internet connectivity, just the peer-to-peer connection. The low range of peer-to-peer, the fundamental flaw, makes it so that they cannot communicate between each other. We add our backbone nodes with that stronger link, and we bridge the network. What we first do in our protocol is overlay a tree structure so that we can efficiently pass messages and know exactly where to send for a given destination. We have a protocol. We are able to join the network in order to optimize backbone connectivity and maintain this tree structure, adding grace to the network in the yellow community. We're able to pass messages just using the Bluetooth connectivity in the yellow community, for example, from Alice to Chris. The single path between any two nodes creates standardized routing and minimized congestion. We are also able to pass messages from Alice in the yellow community to Bob in the green community. This would not be possible with traditional peer-to-peer, and as you can see, it's using B1 and B2, our backbone nodes. If a particular client is not currently active in the network, for example, GAD, we have persistence and local storage that makes it so that when they rejoin the network later, we relay that message to them. We have dynamic updating so that the routing state is constantly fresh and up to date. If a particular node leaves the network, we can quickly rejoin, for example, Eric, their child, to the network, optimizing again for backbone connectivity and maintaining that tree structure. You can see that Eric chose the route that was closest to the backbone node out of his two possible connections. So now Rami is going to talk to you about our go-to-market strategy with our product and some of the evaluations that we've completed.
So in analyzing the products that are already out there in the market, we looked at two main dimensions. So on the left, you can see coverage, and that versus ease of deployment. So on the left, you have these really hardware-intensive solutions, cell towers, walkie-talkies, stuff that has to be set up before the disaster situation actually occurs. But they do provide high coverage. Now on the right-hand side, we have those peer-to-peer apps like FireChat, which have all of the drawbacks that we talked about within peer-to-peer networking. There's also Gotenna, which is a hardware mesh, but it's extremely expensive and requires the users to have hardware on them at all times before the scene of the disaster. And here on the right, peer-to-peer, we feel, has a really happy medium between these two axes. And that's because we're providing high coverage by putting those backbone nodes in to bridge connectivity, but it's also very easy to deploy in that you can actually deploy them after the disaster occurs. So we wanted to evaluate based off of a variety of metrics. So first of all, one great thing about our product is that the communication between the backbones is very configurable. So you can configure it based off of what your needs are in terms of population density in the area that you're looking at. So we looked at a couple of different communication protocols. So for LoRa, you would have a range of over 6 miles, XB over 15 miles, and unlimited if you chose to spend more on satellite. And we'll talk a little bit more about that trade-off between cost and ranges between different backbone nodes. So the time to join a mesh network is less than 10 seconds. So if you imagine like pulling out your phone and on Bluetooth trying to connect to a speaker, it's usually quite quick. The maximum client connections is 7, and the maximum clients per mesh network is about 15,000 if we assume a tree depth of 3. In terms of the max distance between clients, we tested that ourselves and got over 280 feet. And latency between clients and between backbones in terms of how quickly the messages are being sent. You saw there on the screen, it's very quickly, less than 10 milliseconds. So we thought that our product was really trying to target this need well, but we wanted to reach out to partners who actually knew what they were doing, who've been around these kinds of disaster situations. And one thing that was awesome is we were able to talk to FEMA, which is a leading national organization in disaster relief, and they were pretty excited to talk about our product with us. And we wanted to ask them, what are your major considerations when you're looking at these kinds of emergency disaster relief products? And so he basically said to us the main concerns are power and cost. So we wanted to optimize based off of these dimensions to ensure that we're not just creating a random project, but something that could actually be deployed. So first of all, in terms of power and battery usage, so for our network, the major sources of battery is really the communication between backbones and the messages that are being sent. But luckily, we are limiting those to text messaging, and we're using quite low power communication protocols between backbone nodes. We've also built in a number of opportunities to reduce battery usage. So first of all, using duty cycling, and also that tree overlay structure that Simran talked about that really reduces message congestion so that we're not flooding the network with too many messages. In terms of cost, there are 3 major components. So the first of all is we need to make these, if we're saying that we're going to be able to drop these backbone nodes into any disaster situation, then they have to be extremely durable, extremely weatherproof. So we looked at if we were to use injection molding to give weatherproof packaging, that would be about $1 per unit in recurring costs. The other cost would be the cost of the NXP board, and then which we're running the backbone code on, as well as the communication protocols. So LoRa could give you $25, but that's over 6 mile coverage. And then XB has a higher cost, and Iridium with satellite uplink would give you $200, but much higher range. So looking at a specific trade-off graph between cost and range for hardware, you can see that you can opt to do lower range hardware protocols for a lower cost, and then if you could go all the way up to 15 miles for almost $70. And so the great thing about this is, as I mentioned before, you can optimize based for the density of the population you're trying to target. So the government or the emergency responder organization could buy these backbone nodes and then use them for a variety of different situations. So in conclusion, we've discussed a lot, but what we're trying to really aim to show you guys is that we've created and developed this full system that we believe can really bridge these gaps between people and their family and the emergency personnel that they're trying to reach in these very critical situations. Thank you, and thank you to our advisor and to Professor Nankova for her support. And we would love to take any questions.
2 questions about the backbone nodes. Are they battery powered, and what radio service are you using between them?
Yeah, so they are battery powered. The average power draw for client connections is on the order of 10 to 50 milliwatts. And the radio technology we're using initially is XB. So XB power draw is very dependent on the range. So you buy an antenna module, and then you can basically determine any given broadcasting power, right? So if you're giving a very dense deployment, then you don't have to broadcast more than like 100 to 500 milliwatts. And if you want a large deployment, you can go up to about 3 watts, I think, which will give you the 10 to 15 mile range we discussed. The key thing is that we're not like constantly keeping these things powered. We don't have like a super latency sensitive environment, right? It's not key that we always have this up and able to send messages on like a 10 millisecond basis. So we can cycle these antennas on and off and queue messages and only like turn it on every like 100 milliseconds with maybe like a 20% duty cycle, which reduces our power draw a lot and allows us to have a very affordable solution.
Okay, that's all the time we have.
Sorry.
Thanks.